And before the vacation or a break, I was discussing about that without defining the state numerically, there is nothing engineering which you can do. And the definition of that state is mostly pressure, volume, temperature. They became a more primitive because of our senses. And also a simple substance requires any two to be stated. So that's how we need to know the perfect relation between the pressure, volume, temperature, how this relation changes the substance to substance, and is very essential in order to select something for some purpose. One need to understand, when do I go for a water as a working fluid? When should I go for a air as a working fluid? When the air and water being a cheap and available naturally, sometimes I go for a other than these two. You see this one, most of the air conditioners and refrigerators don't use these natural substances. They use some substances which are quite different. Why so? Why these two could not do the job of the requirement? It is very important to understand the perfect, that's what I say, consolidation of sensible features for a substance. These sensible features by human, what are the three sensible features we felt? Pressure, volume, temperature. These are the ones which we can sense easily. So that's how every substance is a now number for us. And for every substance is a relation is the knowing. If I know perfect relation, then I say I know the substance. If I don't know, obviously I am not able to develop the relation. Now you see, the first and foremost thing is called a pressure temperature diagram of a pure substance. So the volume becomes at the background. What is supposed to know is, if I go on changing the pressure and temperature of any given substance, what is happening to the first and foremost, as I said it now, the most of the enjoyments, most of the products are happy with the change of phase. Okay, just by changing the phase, most of my desires will be satisfied. Now you see this particular one. Suppose if I start with the lowest pressure and temperature, that bullet please. If I start with the lowest pressure and temperature, something like here, on an average, most of them tend to be a solid. That is what's called the compact state of a substance, condensed matter. If the pressure and temperature especially is very, very low, obvious phase will be the solid. But from here, if I start doing the pressure, temperature, etc., there is a perfect relation up to a point called a triple point, and starting from so-called the zero, or what is that lowest temperature, only possible if I know this particular state. What I want to say is, when I start from a very low temperature, whatever may be the pressure in general, the solid is obvious, and whenever I increase the temperature at a given pressure, something like I said no, A to B, a solid will directly become a vapor, or when I decrease the temperature, vapor will become a solid. In fact, no, these are the ones which are very useful, some of the applications. The most of the important applications in the modern life is solid room fresheners. So when can I use something as a room freshener as a solid? This particular solid at ambient temperature and the pressure should evaporate whenever it is exposed to the air. So these are called as sublimation or a deposition. If the solid becomes vapor directly, it is called a sublimation. If the vapor becomes a solid directly, it is called a deposition. And the nature is full of those activities continuously are happening. When I go on increasing the pressure temperature along this particular perfect relation, the shape of this line now is an exclusive right of a substance. Water will have some relation, or some other substance will have some other relation, oxygen will have some relation, nitrogen will have some relation, silver will have some relation, gold will have some relation with. It is very important that this is an exclusive right of a substance. And we need to choose whether I need this relation or not. When I go on increasing the pressure and temperature, first time I'll try to see three phases in equilibrium. It looks like the liquid is an intermediate phase for everybody. It doesn't happen below some condition at all. Okay, so this is the one which is the most important innovation, the most important requirement for the knowledge of this one. What is this called? A triple point of a substance. When I have this combination of pressure and temperature in any container with the substance, you will see some liquid, you will see some solid, and you will also see some vapor. All the three phases exist in an equilibrium. So if I supply the heat, solid will become liquid, and if I go on supplying, liquid may tend to become a vapor. So that's how the triple point of the substance is the fundamental knowledge everybody should have. If the triple point of the substance is too high or too low, that decides the natural state of a substance. Okay, we will take these particular examples soon. And also know, by knowing this triple point, and as I said it, know the purity of substance is with respect to our system. So if the substance enters and leaves with the same purity, I consider it as a pure substance. I'm not saying that it should be a single chemical component or it's a mixture of component. That is not there. For me, within my control volume or a control mass, the substance from the beginning to end remains as the same chemical. I consider it to be a pure substance. So that vision helped a lot. So give me a picture, please. Board, whiteboard. Okay. So now you see this particular then, the out of the research in a petroleum product, no, they found what is called a LPG, liquefied petroleum gas, which is supposed to be a mixture of butane and propane. And there may be some more small percentages of hydrocarbons. What is important thing is this LPG, unless I burn, the purity of the substance remains same, but the phases may change. Suppose if we see this mixture as a pure substance and the people started drawing, I don't know why it started, I also wonder how could they get such a relation P versus T. Okay, so then as usual there is a sublimation region, there is a triple point, and afterwards this is the region, this is the solid, and there is a vapor line, isn't it? So we have seen this is called a solid, sorry, this is called a solid, this is called vapor, okay, this is called the liquid region, okay. So if you see a typical mixture, this particular triple point, no, close to ambient pressure like approximately 101 kilopascal, this triple point, not exactly, the close to 101, and this triple point temperature also almost close to 30 degrees Celsius or so, and which is very naturally possible in a nature, getting a pressure of 101 or so. Because of the triple state, you see this particular one, if I take a natural form of this LPG, it will tend to be vapor. Now, if I take LPG from the industry at a constant temperature, if I increase the pressure, what will happen? Vapor becomes liquid. You don't need any kind of cooling at all. What do? You take the natural LPG coming from a petroleum industry and compress it with a compressor at a constant temperature, all the vapor will become a liquid. And this pressure rise is only 14 times, that's all, 14 bar. Now what is the advantage of such a innovation, such a knowledge? And as a vapor, the volume of the gas is very, very high. And the moment it becomes liquid, and the volume decreases 1000 times. What does it mean? You compress it a little, all the LPG becomes a liquid. You take a small cylinder, 1 month requirement of a family available in the small cylinder. You can market it easily. The utility of LPG became so easy. The modern city and modern urban area in many nations became very much possible because of this particular property. You imagine, can you live in a big cities without LPG as a primary fuel for cooking or any kitchen equipment? And all this is, that's how you take a vapor, realizing a triple point will introduce many things. On the other hand, if I take a natural gas, the triple point of natural gas is so unreasonable that even in the buses and cars, even if I compress it to 250 times the atmospheric, it is still gas. So because of which what will happen, having a storage for more than 8 hours in a bus or a car is impossible. So that's how CNG buses for a long distance is a big threat. Within an urban area you can move because there are so many CNG stations in general possible. You imagine the LPG can go to the remote area. There is no problem. If you go to the remote places in something like Uttarakhand, where I have visited, there are many remote villages where there is no electricity, but they get LPG. Why? Because the storing a requirement of 1 month, 2 months is deadly cheap. And the pressure is not very much, 14 times atmospheric is easy to handle. Very important to know this relation. If I had not known the triple point of LPG, perhaps the utility of LPG will be very low. Modern urban areas will suffer a lot for fuel, and getting a wood transported so much is physically impossible to develop a well-developed nations. Going back to the slides, now you imagine the entire thing. Give me the bullet. Now you see this particular one. The moment I reach the triple point, afterwards what happens at any given pressure, if I go on increasing the temperature at a isobaric or so, that is easy to understand. Something like you see this one, EF line. Suppose if the temperature is very low at a given pressure, it will be solid. Slowly if I increase the temperature at a constant pressure, and there will be a change of phase which is not visible on this. Why? Because whenever there is a phase change, what can change is the volume, but we are drawing only the pressure versus temperature. The volume changes are not visible. It looks like the pressure and temperature does not change during the phase change, and afterwards there is a liquid. If I go on further increasing the temperature, the liquid will reach the saturation temperature, then start becoming the vapor. Then if it is a more and more high temperature at this pressure, when the temperature is reasonably higher with respect to this point, then it will behave like a ideal gas. A simple relation between PVT is possible. Suppose if you are close to this line, the nature will not be ideal. The complex relation between the PVT exists. So that's how the fundamental knowledge, every nation will have a separate department which will do this kind of knowledge creation. Maybe Bureau of Indian Standards, and similarly every nation. If you go to America, there is an organization called NIST. You can go and see the expansion. The duty of them is to create all the knowledge of PT for a new substance. If I invent a new substance, I should get this relation before I think it is useful. Suppose if I go to the line called a CD, okay, so the liquid continues to be continuously changing like a vapor. I'll come back to this particular one a little later. Now going to the next level of knowledge. The first level of knowledge is to know the PT relation in the entire range possible. Very, very low pressure to very, very high pressure. Very, very low temperature to very, very high temperature. In the entire domain of PT, you need to know this particular, I think, 3 fingers. What is the shape of these 3 fingers is very important. One need to develop an equation. Let me tell you the low pressure behavior of the substance, okay, which is called a condensed matter relations. You see the general behavior of solids. The solids are called incompressible substance. What is the meaning of this one? If I take this particular solid, I am crushing till it fails. I don't see any change in the shape at all. It may fail, it cannot take any amount of force. It looks like the change in volume with respect to the force is limited. That's why this is called incompressible behavior of the substance. At the same time, if I heat it, the changes in volume are more recognizable. So it looks like the volume, which is the more tangible and sensible property of a substance, which we can easily see and feel, is a strong function of pressure and temperature. And that helps a lot in constructing many kind of equipment in general. You imagine, if I am constructing a building, the material used in the building should be such that the change in dimensions with respect to the load or a temperature should be bare minimal. Otherwise what will happen? And everything will collapse. You cannot live happily. If directly continuously volume changes with respect to, there are 10 people sitting in the room, there is a small height. The moment there is 100 people sitting in this floor, ground floor will get crumbled. That is nonsense. So you need to have that's how the solids have a peculiar application. As I said, change in volume with respect to pressure is infinitesimally small. With respect to temperature also small but not negligible. The hence increase in temperature or a pressure required for a finite change in volume is volume, area or a length. So if I want to change a volume of a solid very much, you need a high pressure change or a high temperature change. Otherwise, getting all of if you are doing some kind of forging, you might have done a blacksmithy in your lab. Unless you increase the temperature a lot, and changing the shape of a metal is very difficult. So all these things will lead to the thing. So in an ideal solid, which you learned in the school also, there is called a Hookean solid, which follows a Hooke's law, where the rate of relative change in the length or a change in length per unit length is directly proportional to a force per unit area. These are the most important substances. In fact, the realization of this behavior led to massive growth in the industrialization. Okay, thermal expansion of solids. This can be used very well, and sometimes you need to respect the thermal expansion of the solids. If you don't respect, then there will be a serious failure which will happen. I'll show you some pictures. As the thermal energy in the solid increases, I told you the temperature is the amplitude of vibration of a molecule with respect to a mean position. Whenever you increase the temperature, amplitude is increasing, because of which intermolecular distance increases. As a whole, the volume increases for the same mass. So this causes the solid to expand. So there are three kinds of expansion. Sometimes if I take a one-dimensional solid like this, whenever I increase the temperature, change in area is negligibly small, but length will be very good. This is called a linear expansion. Suppose if I take this kind of an object which has a good width and good length, but the thickness is small. In that case, the area changes are very significant, but change in thickness is negligibly small. If I take a bulk object of something which has a equal dimensions of weight, etc., then perhaps volume expansion is important. The bulk changes in the entire thing. That's how the solids sometimes I can use it based on the linear expansion, sometimes superficial, that is called area expansion, or cubical expansion, depending on the application. Let me see whether I have a good examples for you. You see this particular one. Suppose if I am constructing a long bridge, and if I make the entire bridge a single concrete piece, what will happen? In any area, there is a peak winter and peak summer. During the peak winter, the change in length will be significant because it's a long bridge going through. And during the summer, there will be a increase. That's how every bridge, when you travel on a road, you will see suddenly a kind of a jerk coming on your vehicle. Why? He'll purposefully give a gap which will take care of expansion and contraction during the summer to winter. So if he makes the entire bridge a single piece, and during the summer the entire length increases, the curvature changes, there will be cracks. During the winter, entire length decreases, all the pillars will be bent towards, and there will be a failure. That's how every bridge, after a few distance, they'll give a gap. In the gap, they'll fill that material which easily get crushed or elongated, because I can't keep it open. Then there is a danger. All the vehicle wheels may get stuck into that, not a smooth travel. You see, every civil engineer should understand this principle. If he doesn't understand, what he is supposed to understand, the kind of materials used in the construction of flyovers or bridges, what is the thermal expansion coefficient? So that's how every 50 meters I should give a small gap, or every 100 meters I'll give a larger gap. Then he has to see which is the economically, giving a gap between every 50 or every 100. That's how the technology to technology, material to material, this gap changes. But on an average, you cannot have a long flyovers or bridges without a gap. So thermodynamics talks about the engineering requirement. Okay, so now for that one, you need to know this relation. As I was saying, the volume is a function of pressure and temperature, or a pressure is a function of volume and temperature. Most of the time now, this relation is useful in the civil engineering. Whenever I am doing a civil engineering construction, suppose if you have a long multi-storied buildings, they will have a pillars and the beams. So whenever you have a pillars and beams, no, after some length, they have to give a gap for taking care of the thermal expansion, etc. The civil engineering is the one who uses a lot. Because of this one, no, I'm not telling a lot, but these slides are available on my website on MEL 140. You can always download and read if there are civil engineers. But for a mechanical and other engineers, this particular one is of least interest. Okay, you see this one. You know the ideal gas equation, no? How the pressure, volume, temperature are related. When it comes to the solid, the relation is such a complex thing. The pressure, volume, temperature relation is unreasonably complex, not like a simple behavior at all. And all the civil engineers, some of the mechanical engineers who work in a forging, all should know this relation. Then only, suppose if I am having a mild steel, I am having a silver, and especially the goldsmith, should exactly know what should be the temperature to make a beautiful configuration of some ornaments. So for everybody should understand this relation to come up with a perfect change in shape. If you take a lump of a gold, that is not the one which you can wear in anywhere. That particular lump of a gold should be converted into plates, sheets, cups, or wires, and those wires should be curled nicely, then only it becomes a good ornament. So for that one, he need to understand how much temperature should be increased. After increasing the temperature, how much force should I apply that perfectly I get this shape. So there are many areas, means fashion industry should understand this one for all the kinds of metals. You do, those people who did a graduation or a master's in a fashion industry of ornaments, they should understand this relation. Every time they come up with a new materials which look beautiful, but they need to know the relation also. So industry goes in a many ways. You can see this particular one. If I know this relation which I have shown, there are constants called B naught, eta naught, and alpha naught. There are three properties which will decide the nature of this particular substance. So then you will understand, in order to change a shape, increasing the pressure is economically good or increasing the temperature is economically good. You need to understand based on these properties. For a mild steel, changing the shape only by the pressure is very costly. It may spoil the mild steel. Whenever I want a large change in shape, better to increase the temperature, what is called a hot forging, hot forming, hot rolling. Then no, you will get an economical thing. But only by increasing the pressure if you want to do, that may lead to the breakage. Okay, so that's how very important to know these important properties. You see this one, when it is a gold, the B naught is 16.6 and the alpha naught is 4.25 and the del beta by del B by del B, P, which is called eta naught, is this. You can see this one. Suppose if I take the gold, sodium chloride and xenon. There are three different materials. Which one is easy to change the length by pressure? Xenon. Xenon is such a soft material like chocolate. Apply a small force, it changes easily. Now you see a sodium chloride. If you see a sodium chloride, can you change the shape of the salt in your hand? If you apply too much force, it may become a powder. And the gold, no, with ordinary forces, difficult to change the shape. That's why there is no industry in the world, fashion industry in the world, which can make a gold ornaments without increasing the temperature. Why? The gold requires a lot of pressure. You see this one. This is a measure of how much change per a 10 to the power of 6 pascals. Okay. All these things are very important to appreciate. Now, this is the simplified relation between the volume and temperature pressure. The one is more complex. People try to simplify. You can develop a various relations to start with. Okay. So at the end of the day, if I see the three-dimensional region of any substance, no, will have pressure, volume, temperature domain. If the pressure and temperature and volume is lying within this particular area or within this particular volume, then you can say it will be solid. Now what is the important thing? Let us say I take some thing like a water. So I'm keeping the same pressure, okay, here, and the same volume, okay. So, but I'm going to the temperature very large. It is impossible to have an ice at this condition. Why? You are outside that particular behavior. See this one, every substance is intelligent. We say no, they don't have a life, but they have a very smart thinking. It is impossible to have a water, ice at this pressure and temperature. Suppose at this temperature, if you want to have ice only, what should I do? I should change the pressure. If I change the pressure, perhaps it is impossible to have the solid or a vapor. Very important to know that every substance will have a kind of contained volume. Whenever you are outside that particular shape, the change of phase occurs. Now, you see this one low pressure behavior of the solid. I told you, sublimation and deposition. So there are many substances that directly a solid becomes vapor. Directly vapor becomes a solid at low pressures. There are many applications which will occur, and the nature has a beautiful characteristics like this. Let me show you what happens in the nature. Okay, these are the general thing. I'm giving the knowledge for the sake of somebody who is interested in the shape of this particular curve, the PT diagram. Okay, but as a common thermodynamics, most of them may not be interested. But I don't want to create that kind of ignorance that this is not important. There are many industries which are interested in knowing this relation between sublimation curve. So that's how I'm giving how the typical sublimation curve looks like. For every substance you will understand, and especially the sublimation curve for water is very important. In fact, the nature has a full of examples. All of you know, whenever you open the fridge, if you see in your freezer, always there is a peculiar shapes of ice. The ice doesn't look like a ordinary flat thing, and it will have a spikes, beautiful configurations, etc. happens. Why? Because the relative or a partial pressure of water vapor in the fridge is always lower than this most of the time. Now because of which what happens, you imagine. So you open the freezer, and hot food you are keeping in the freezer. Now because the food is very hot, there is a lot of moisture which will evaporate, and the steam will occupy the freezer. But the partial pressure of the steam is very low. And the moment this vapor is subjected to cooling because of the freezing, whatever refrigeration occurring, it will at a constant pressure it will move it to low temperature. What is happening? Suddenly the steam is becoming a solid. So because it is suddenly becoming a solid, there is no liquid phase in between. The shapes are beautiful and peculiar. And if you see the frost, always very peculiar shape. And I can show you the nature. You see, in a peak winter in many places, and the temperatures are going very low. All of you know the partial pressure of water vapor in the air is in general very low. When the temperatures go so low, all the water which is available in the form of vapor in the air will suddenly become a solid. You will see such a beautiful pictures in the nature, very peculiar. And this is called a frosting, a frost formation or so. So afterwards, the moment I cross this particular triple point, the solid has to melt. Without becoming a liquid, a solid cannot become a vapor at all. There is some phase in between. The first time you see three phases. So that's how this particular shape, no? You see this particular one. As I go on changing the pressure, the slope of this one is changing. This is called a melting curve. Many a times I need to know how the melting curve changes. All of you know, water has a peculiar behavior. You might have read in the school also. It is something unexpected, a nasty behavior. So what is happening to the water? The water, if you go on increasing the pressure, the melting point decreases. Now because of which what do? All the skating people, they have a special skating shoes. So below this one there is a sharp edge. What do? Because of that one, whenever you stand, And you need to have the technique. Whenever you want to move freely, you have to press the foot. Then automatically you are increasing the pressure. Because you are increasing the pressure, at the same temperature, ice becomes water. Suppose if you want to stop in between, suddenly what you should do? You should slowly create a lightness in you. Then what will happen? The same water will become ice at a constant temperature. That's how the entire skating game uses this particular principle. If they don't know this particular relation practiced, I am not saying that they are reading this one, but by the virtue of practicing, they try to understand when should I apply the pressure. When they want to move very fast, what should they do? They apply a more pressure. Suppose let us say a skater is climbing. A skater who is a climbing, if he doesn't press too much, what will happen? He has to move against the ice. Very difficult. He cannot produce that much energy at all. So whenever he is climbing, he should apply more force so that there is a water, he is going through the water with this. Suppose he is coming down. If he applies too much force, what will happen? All the ice will become water, he will fall. He will lose the stability. In that case, he has to lift himself by inhaling air or so, he has to lift it and try to have less amount of water in the slot. Then automatically it applies a brake. In the path, if there is a ice, there is a brake. Very, very important. Like I am giving you simple examples, but the industry will have variety of this. Okay. Now you can see the solid, liquid phase. The molecules are little separated. I have a small animation, like always there is a Brownian motion, which you know. You see this, the PVT relation of the liquids. They are not very simple, but they are much simpler than the solid. So what is the peculiar behavior of the water? Whenever I have a liquid, when I pour into a vessel, it will take the shape of the vessel, no doubt, but the volume doesn't change much at all. So liquids have some kind of peculiar behavior. Changing their shape is easy. You don't have to do anything. You change the vessel shape, automatically they'll take the shape. But changing the volume as a number is impossible, or again it is like a incompressible. Even the liquids also require a very high force to change the volume. So the solids and liquids are in general called as a incompressible. But the difference between the solids and liquid, you know very well that they can change the shape easily, but not the volume. Number, that's how I know in engineering, the number is more important than the qualitative. Okay, the change in volume is important. The change in shape may not be important in a typical engineering applications. So, but the most important thing for a common thermodynamic scientist or a mechanical engineer or any kind of thing is understanding here onwards. You see this one, suppose if I have a liquid water and if I put a piston and lot of weight at the same temperature, what I mean is these two are at the same temperature. Okay, the temperature is same. Can I have a small pen for a while? So you say that the both are at the same temperature, T infinity. In both the cases, the temperature is same. Suppose if I put a lot of weight on the piston, all will be liquid. Suppose if I remove all the weight at the same temperature, automatically the liquid will start evaporating. This is the one which is called the pressure temperature relation, which I have shown you know. The relation which we has means at a given temperature, if I decrease the pressure, it will evaporate automatically. But of course, whatever energy required should be supplied. So there are two ways of boiling something. One is by decreasing the pressure, one is by increasing the pressure. Now you see the milk industry has a two ways. Suppose if I want to produce a milk powder, what should I do? All the water in the milk should be evaporated, then you will get the milk powder. One is you go on increasing the temperature till all the water boils. So you are heating the vessel. So whenever you increase the temperature, the milk molecule will also get affected. Perhaps milk molecule may get burnt. All of you know, when you are cooking a food in a vessel with a flame, if you are not careful, some of the food will get burnt. If you eat a burnt food, and it will create a lot many problems. For a babies, it is more dangerous. They may get a serious problems to death also. So what is the better way of producing a milk powder without any problem? You take the milk, you seal the entire vessel, slowly decrease the pressure by having a suction pump. Then what will happen? Whenever the pressure goes below a point corresponding to ambient temperature, what will happen? All the water will evaporate. Now, without spoiling the milk molecule, without burning anything, the babies can get a good quality baby food. Very important. Whenever you are producing this, then you need to see the economy. How much energy is consumed by this vacuum pump? Is it worth doing? Otherwise, you can have an intermediate deal. What you do is increase the temperature of the milk by 20-30, so that will not burn any molecule at all, and then start decreasing the pressure. Then what will happen? It is techno-economically viable and also safe. So because too much increase in temperature is dangerous, but too much decrease in pressure is costly because you need to have a very big pump and electricity consumption also. So in a typical industry, they'll optimize. First they heat the liquid to a small something or a milk, and afterwards decrease the pressure and get a cheap way of producing the milk powder. Otherwise, milk powder will be much costlier than the milk. Now let us go and understand this particular one. I am starting this one because this is the most important thing for general mechanical engineering or many of the applications which happen in a general life. So the first one I am doing a state 1. What is the state 1 here? I am taking the water at a 20 degrees Celsius. The piston kept on this one is such that it is literally floating without having anything. So what will happen? Whatever atmospheric pressure, no, that is acting on the water. So because of that, what is happening is, if I see the diagram, can you give me whiteboard? Suppose now what I have a vessel, okay, which contains the water, and on which I put a piston, and this piston is such that it is a very light and floating. The actual pressure is only the atmospheric pressure, whatever ambient air pressure, no, that is only acting, and this is all liquid, and this is at a 20 degrees Celsius. Why it is liquid? Suppose if you see the PT diagram of water, so this is the triple point TP. Afterwards, this is called a solid to liquid line. This is called the liquid to vapor line. Now if you see the situation, this particular condition is somewhere close to this, because the pressure is higher than the triple point, the temperature is also higher than the triple point, because of which the natural state of water at ambient pressure and temperatures are mostly liquid. This is a beauty, you see this one. If the water doesn't, in fact I always wonder what is the natural combination, why we need so much water, why all the living substances are interested in water only, nothing else. Because the nature created the species in such a way that the one which is naturally available as a liquid should become a source of living. Otherwise what will happen? If somebody says ki liquid helium is essential for humans to live. Now that liquid helium to be liquid will happen at a 4.4 Kelvin. Means none of us can live happily. There are some fantasy stories, no? There is a planet called Jupiter. In the planet Jupiter there are some species, aliens or whatever you name you give, they inhale CO2 and live happily. They drink CO2 and happily. That fun can happen. So it looks like the liquid became liquid water became essential for a human life because it is naturally liquid and you can afford to have that particular liquid. So that's how. Now this particular thing, what I am doing, I am using some kind of what I say, a Bunsen burner, and slowly heating this one. If I go on heating at this one, and when the temperature reaches around 100 degrees Celsius, suddenly piston will rise. Till that point, piston rising is almost negligible. And after this particular point, the rise in piston is very fast, one. Now I see a peculiar behavior here. So here to here, no, from state 1 to 2, whenever I add some amount of heat to heat it, the temperature is also changing. But the change in the piston position is negligibly small. The moment it reaches 100 degrees Celsius at this pressure, the change in temperature is zero, but volume started changing. Very peculiar, no? The relations are suddenly re-established. So till some point, the volume seems to be not a serious function. Pressure at temperatures have a very nice behavior. Any change in temperature is changing the, any amount of heat addition is changing the temperature. So this kind of behavior is the one very nice, very important to realize. If I go on increasing the temperature, what is happening? You see this particular one. So the first time when the water reaches a temperature of 100 degrees Celsius, though I am adding a lot of heat, temperature does not change. But the piston will start moving very fast. The relative means for a continuous heat addition, the piston is suddenly jumping up and then why the piston is getting a suddenly a motion and why temperature is not changing? For a first time when they did, it was a big surprise. According to the literature, the first engineering science, or first engineering knowledge is called production of steam. Understanding that there is something like a steam behavior. Now you see this particular one. If I read one by one, very important, all of you also focus. At state 2, the liquid has reached the temperature at which it begins to boil. So it is impossible. Why? It has reached the edge at this particular pressure. Okay. So if I come back to the same picture now, can you go back to that picture? Keep the same picture. Now you see, so the pressure is constant because I am not putting any weights. The slowly I am adding the heat, adding the heat, adding the heat, and reach this particular a kind of a critical point, you can say. It is not called, this is called a saturation temperature. Afterwards, temperature change doesn't occur for a very, very long time. And on a PT diagram, it is cut. Though I am adding the heat, as if somebody is stopping you, nothing is happening. Pressure and temperature, because I kept the pressure constant, temperature doesn't change. Though I am adding the heat, though I am adding it, it was a big surprise. Who is stopping the temperature to temperature not to increase? I am adding the heat, temperature is not increasing. So this became a big wonder, a big surprise. And for a long time, the jumping of the piston was felt happily. They could not feel that there is a jumping of a piston. Perhaps instead of temperature, something may be happening. So that's how the people said. So whenever the temperature increases, whenever I add the heat, I say it is a sensible. And whenever the temperature doesn't change when I add the heat, nonsense. They don't want to use the word nonsense. They use the latent. What is so latent? What is something which is not visible, sensible? That is the one which made the common researcher to confuse. They give all the heat I supply at this particular point, is just latent. Gupta hai. In fact, in a typical Sanskrit or any Indian language, Gupt. What is so Gupta? What is so secret? And below that one, any heat addition is changing a temperature. In fact, this created a marvelous change in the lifestyle. The day they understood this particular one, the lifestyle on the earth has changed totally. The people used the water to boil the food, and boiled food was better for the health than unboiled. The people health increased, their digestion system became very clean. The number of diseases, number of deaths automatically came down without any medicines. The human wanted this kind of lifestyle. Why? They are naturally extrasomatic. The nature created us to such a way that if you use more energy, you live happily, otherwise you will have problems. I told you in the first day, we are very peculiarly designed by the nature. Okay, so this is the whatever I explained. Afterwards, what is happening? The volume of the mass of vapor is increasing. The mass is, and the liquid is decreasing, and all the liquid is slowly becoming a vapor, and there is a jump in the piston position. And if you have a transparent thing, you see this particular one. If I go on doing, after some time again some temperature started increasing. So that's how the first time the temperature start increasing again. Now you see this one, Initially I took the pressure of an atmosphere and 20 degrees Celsius, the substance is water and the state is liquid. And when I start heating, the water temperature was changing very fast, but the piston movement was negligible. Suddenly the piston movement became very large, and temperature was not changing at all. And so again, when I go on adding the heat, the first time I got a peculiar behavior. For a small heat addition, no, volume changes more and temperature is also changing more. So that's how the people wanted to recognize this one. The first time when the temperature was not changing, volume started changing is called as saturated liquid temperature. The first time, again the temperature, volume both are changing is called a saturated vapor point. So from a saturated liquid to saturated vapor, temperature cannot change unless you change the pressure, but volume changes tremendously. What is the advantage? Where all I can use, let us use all those applications. After the saturated liquid point, any addition of the heat is changing both the volume and temperature both significantly. Now you see, after all, the substance is only the water or H2O, whatever you call it. At some level, addition of heat will only change the temperature but not much volume, maybe marginal, and suddenly there is a region where addition of heat changes the temperature nothing. It looks like infinite amount of heat you give, suddenly not happening. So the temperature doesn't change, volume changes a lot, and afterwards again there is another point, critical point, where the temperature volume both changes nicely. Okay, very peculiar, means this is the one which attracted every creator, every genius. Kuch to karna hai, I should do something with this. And the people started thinking, they started boiling the food, and many peculiar things, Boyle's law, Charles' law, everybody got an attraction. You can see this particular one. So initially, you see, the change in volume is very small whenever temperature changes. In fact, no, I am purposefully drawing very large. Later I will show you real properties. 1 to 2, no, volume change is negligibly small. I cannot draw on a diagram at all. I am overshowing just to show that there is a change. Afterwards, the temperature remains constant. I am adding heat, I am adding heat, I am adding heat. This is a constant pressure heating process. Okay, very important, constant pressure heating process. The slowly the entire thing is changing. The first time, again, what is happened? Here onwards, see, as far as heating is concerned, same. I am burning the fuel, burning the fuel, burning the fuel. There is no change in attitude of burning. Even then, the substance is behaving thing. It was a surprise to all the ancient inventors who have so much concern about the science or a behavior. Now here onwards, any addition of heat, no, not only changing the temperature, even the volume also changing. Very peculiar, no? I am adding the heat at a constant pressure only. I am not putting the more weights. The volume is increasing significantly, temperature is also significantly increasing. Why? This particular substance has such a nice behavior. Why this particular fellow is so rigid? Whenever I am giving a heat, why it doesn't change the volume at all? Why this fellow only changes a volume but not a temperature? Why this person has a kind of a democratic behavior? Because I have a 3 parameters which I can sense happily, easily. Pressure, volume, temperature I can sense. My entire knowledge is I am able to sense what I am not able to feel. So initially this phase I can sense temperature, volume changes are negligible. My senses do not notice even unless I have a hi-fi instrument to measure it. Here I could easily see that volume changes tremendously, temperature doesn't change. I'm not happy with this also much perhaps, maybe happy sometimes, and this is the one which has very nice behavior. That's why I know this phase of substance philosophically called as a bountiful state of a substance. Why? It gives a kind of openness. It doesn't close any behavior. It's open-minded. Whereas this particular one is a closed mind, only temperature change but not pressure. It's not very open-minded. This is the one not open-minded. Volume changes so much but temperature is contained. Why so? Somebody who is a open-minded should open to any change if it is a good. And that's how no, this state of substance philosophically called a bountiful state of a substance. And if you depend on this state, no, it will do wonders. You can change your lifestyle a lot, and how people recognize, we will see slowly, step by step. Now, what is important is the 2 to 4, not changing a temperature at all became a big nuisance, because the change in volume is the one which is a substance specific. If I take 2 kg, more change in volume. If I take a 10 kg, more change in volume. If I take only 10 grams, change in volume, I may not be noticed much. But if pressure temperature changing is a very good behavior, isn't it? Okay, because both are independent of thing. I told you, no, intensive properties, extensive properties. If I depend on intensive properties, doing experiment, creating a new knowledge is easy. Now you see, if I want to depend upon a volume change, unless I take 10 kg of water and heat it, the change in volume measurement cannot be precise. Now, suppose if the pressure temperature is only the one I have to measure, whether I do 10 grams or 1000 kg, the result is same. Means with a less expenditure, I can do the experiment perfectly. If I want to heat 1000 kg of water to get some knowledge, how much fuel should be burned? What is the size of the boiler and heater? Is it viable to know knowledge? And so that's how now intensive property based knowledge is very good. So that's how the people know the only volume changing, not temperature changing, became a discomfort. Okay, so that's how they wanted to do something very different to this. Now you can see the entire behavior. I'm giving you a specific example. Okay, I'm keeping the pressure temperature. If I have a temperature 85, so if the pressure is 57.83, what does it mean, saturation pressure? If the pressure is below this one, it will be liquid. If the pressure is below this one, it will be vapor. If the pressure is above this particular one, it will be liquid. Or for a given pressure, if the temperature is lower, it will be liquid. If the temperature is higher, this. Now you see this one at 85 degrees Celsius, at a constant pressure, if I go on adding the heat, the temperature doesn't change, you see the volume. Initially volume of liquid is negligibly small, 0.001 meter cube per kg. If I take a 1 kg of water at this particular pressure and temperature, it is not more than a liter. And the same thing, when I add the heat, pressure doesn't change, temperature doesn't change, but see this one. The volume is increasing 2828 times literally. So same 1 kg will have a volume of 2828 liters. But temperature and pressure are same. Very peculiar. The people try to understand why such a large change in volume. What is the advantage of these particular large change in volume? And how can I exploit this particular one? But more and more is, again, if I increase the pressure to 70, then boiling point becomes 90, and the change in volume, you see this one, almost 1 liter to only 2.367. So there is a drop in the change in volume. If I further increase the temperature and pressure, and there is a further drop, you see this particular one, there is a serious drop in increase in volume possible. If the pressure and temperature are very low, 1 liter becomes 2828 liters, and I increased the temperature only by 10 degrees, isn't it? And I increased the pressure by 57 to just 84 kilopascals. But you see the change in volume, 2828 is becoming just 1982. Now again, this is a new knowledge. So whenever a saturated liquid becomes a saturated vapor at a low pressure, the change in volume is enormous. When the same liquid, everything same, when the change of phase occurs at a higher pressure, the change in volume is small. And this is decreasing. Then see, all the enthusiastic minds, they say ki, what happens if I further increase? If I further increase, the curiosity has grown to a level of that and produced a special scientific theory. You believe me or not, in the history of science, the first scientific theory is producing a steam. What happens when I change the pressure and temperature? It is the first kind of science. Because otherwise before that what is happening? I am only saying water, water will evaporate. That is a descriptive knowledge. Now this descriptive knowledge is converted into numerical knowledge. What is the first numerical knowledge you see? The water and steam are typically used as a heat carriers in the heating system. The moment they understood, no, it became a kind of means of production. You can make the medicines by boiling, you can cook something, you can heat something, many things are possible with the water. The first and foremost note is water boils at 100 if you don't apply any extra pressure. Means I am keeping a light piston to close, but there is no pressure increasing at all. Suppose on the piston, if I put a more and more weight such that the pressure of the liquid or a system is 10 times more, what will happen? You see this one, the liquid line, liquid remains as a liquid for a long temperature, means temperature increases up to 179.9. At 179.9 again temperature stops. So you see the peculiarity of this behavior, and the people wanted to understand what is this one. At a constant pressure of 10 megapascal, the saturation temperature is 311 degrees Celsius. Mean it is a 10 megapascal, means 100 bar, and the temperature is this one. So very interesting to know this particular curve. Can you please show the same picture? Now you see this one, this particular line, no, has again the P is directly proportional to T. Means the, what is this P and T? This is a peculiar thing. Below this particular condition, when I am this side of the line, the temperature changes, volume doesn't change much. When I cross this particular line, go away, volume, temperature both will change. At this particular combination, only volume can increase in this direction, but not temperature. So means this relation was very attractive. The people got stuck to this one. Suppose let us say I want to cook some peculiar medicine. To cook that peculiar medicine, no, I have to keep the temperature of that particular thing 179 for a very long time. Now how to put exactly 179? What is this one? You create a pressure of this one and enter into this particular region. Whatever I do, no, whether I cool it or I heat it, nothing will happen. The temperature will remain constant. Means I can create a large temperature. You see this one of the funniest product which can happen. Because of this particular behavior, the home delivery of food became very easy. Now you see this particular one, unless the food becomes hot, food remains hot, doesn't remain hot, can you get a home delivery? Nobody will prefer a home delivery at all. Now that's how all the pizza boys or a idli dosa, whatever you want to order. So at the back of their scooter, no, they'll have a peculiar box. This box is not a simple box. Now this box will have a double wall, inner box and outer box. The space is filled with a special kind of liquid, a gel kind of liquid. So what happens, and outside is perfectly insulated to decrease the any kind of heat losses. Now what they think, so suppose the pizza shop, he'll put a hot pizza inside this particular box. Now the pizza is very hot, so it will cool and give the heat to this particular one. So always know this particular thing is selected in such a way that the pressure, so this is, I showed it to you, know, this kind of behavior. Okay, so this particular one at ambient temperature of 30 degrees Celsius is, this is the one. So whenever there is a heat transfer from the pizza to this one, it will move along this particular line. Now the pizza cannot heat for a very long time, pizza will slowly get cooled. Now you see this particular one. Now the moment pizza decreases, all the liquid will remain at this particular temperature. And now the pizza is kept at a constant temperature till it is delivered. Not only that, let us say in spite of insulating, there may be some heat loss to the environment because ambient temperature. So even if it is a heat loss, the entire heat loss is here only. Means if the pizza is delivered before the liquid reaches this point, it will be hot. Now, what is the pizza delivery and home delivery? The entire business becomes so popular. Otherwise, what will happen? If everybody says ki, unless I go to the pizza house, I can't eat pizza, the number of people eating a pizza will be less. क्योंकि यार every time going out, taking a taxi, going to the shop and coming back, lot of time is wasted. Eating pizza takes 10 minutes, traveling to pizza shop and coming back take 2 hours. I don't have a 2 hours for this. Then I'll say, no, no pizza, let's make something at home. The entire food business will suffer. Instead, I'll make a phone call. I'm doing the work. After doing a phone call till pizza is delivered, I'm doing my own work. I'm not waiting for the pizza etc. at all unless you are too lavish about the pizza. Okay, so you see this one, having a knowledge of this one make a food industry so powerful. The entire business became so many people get employed. And you see this one, the pizza is an Italian taste. You can eat in any small town in India. Why? This entire thing grew to such a nice level. Means by keeping the entire thing always in the zone, whatever temperature at which pizza tastes good, that can be kept from the point of starting to pizza delivery. You see the level of confidence and technology that Domino or some other, whoever may be, he says ki, if I deliver the pizza lower than this temperature, muft mein de dunga. I mean, he's so confident about the knowledge. He knows that he can deliver the pizza before this particular point reaches this and gets cooled. Afterwards, what will happen? Temperature will change. Now the pizza will get cooled. I don't like to eat that pizza at all. Very, very important. I'm giving a very funny or interesting examples for a common life, but thermodynamics does such a common life and creates a new business avenue. Without this one, perhaps I don't think a food business is possible anywhere on the globe. That food business will be limited. Okay? Done? Oh, sorry. I'll stop it here. We'll continue the next state most important for the sake of product development. Thank you. Thank you very much.